All right. So, Algebra 2, fall final exam, part 1. So tomorrow we'll do part 2. The goal is to get through as much as we can together. The rest will be recorded and you can watch the rest of part 1 on your own. Cool? All right. So here we're going to do. We're going to start here with determining whether a graph, a table is linear, quadratic, or exponential. Okay. And there are rules that we learned for each one of them. Okay. So looking at the first one here, the first thing you're going to do is find your change in your X and your change in your Y. Does that ring a bell? So to get from here to here, we added 1. To get from here to here, we added 1. Here to here, added 1. Here to here, we added 1. Agreed? All right, what did I do on the other side? I added 6, right? Added. Then I added 18. Then I added 54. Nope, not yet. You always find the common difference first. Or if there is one. So you check that. And I think that's 162. Okay? So when I find out the change in Y or the change in X, so I have my 6 over 1. I have 18 over 1. I have 54 over 1. And I have 162 over 1. Is there a relationship between my ratios? Like, how can I go from 6 to 18? Times 3. How can I go from 18 to 54? Times 3. How can I go from 54 to 162? Times 3. So if there's a constant ratio of change, what does that mean I have? It is exponential. It's going to be exponential. Okay? And that's because we have a constant ratio. Meaning that there's something that I'm multiplying by consistently between the differences. Okay? So therefore our rates of change, that's what we're going through. Nope. It's just knowledge. You being prepared. What? Nope. All right. So same thing here. Again, for all of these is going to be a change of 1. Do we see that? So each one down is going to be a change of 1. On this side, what is our change? All the way down it is plus 4. So in this sense, when I take the ratio of each one of these, it's 4 over 1, 4 over 1, 4 over 1, 4 over 1. What do you notice now? It's constant. So therefore, it's linear. Okay? It's a constant, which means that this is our what for our linear? It's our slope, right? That's our slope. Constant ratio? Would you? Yeah. Okay, how do you know? And you could just write constant rate of change. Yes. This one is just, there's no change. Like they're the same. They're constant. That means it's the slope of the linear. Yes, your first difference is the same. All right. No, it's from the second week of school. So here we go. Again, it's plus 1 all the way down. But notice here, when we take the difference, what's happening here? We get 3, then we have 5, then we have 7, and then we have 9. So there we go. My first difference isn't the same, but when I have my ratio, 3 to 1, 5, 1, 7 over 9, 7, 1, 9 over 1. What's happening now when I'm finding the difference? There's a second common difference, right? So therefore it's a what? Quadratic. We have a second common difference. And this one's because it's addition. So here on this one, our rates of change have our addition, right? Sure. All right. Do you think you could be able to do this? Identify an exponential, linear, or quadratic table. Yeah? All right. We've done it. You're right. Okay. The next thing we talked about moving on into the semester, we talked about being able to read scatter plots and determining whether it's positive linear, negative linear, quadratic, or exponential from looking at it. Okay. So keeping that in mind, what each shape looks like, we're going to outline our trend and determine what type of graph do we have. Okay, so starting with the first one, if I try to follow the trend of the scatter plot, what am I creating? A positive quadratic. Do you see that? It's smiling at you. It's happy. Okay, if I try to create a trend line following the flow of, we have a positive linear. Okay, if I try to follow the trend of what's happening here, there we go. Okay, and then I try to follow the trend here, we have a negative linear. Okay, are we good with scatter plots? Okay. Next, we're going to average rate of change. When we talk about average rate of change, we talk about that's our change in our y over our change in our x, right? So when we talk about average rate of change, it's not the exact same thing as slope because it can be different from point to point. Does that make sense? So for average rate of change, what you're doing is your y2 minus your y1 over your x2 minus your x1. Do we remember that? Okay. So if I had a scatter plot, for example, I have a scatter plot. I can choose any of these 2 points. Are they guaranteed to have the same average rate of change? No, because the slope that connects these 2 points may not be the same slope that connects these 2 points. Does that make sense? Okay. And so your average rate of change is going to be different depending on the point selected. Got it? All right. Let's keep going. So for our example for average rate of change, we have here, determine the average rate of change from 2010 to 2013 of these gas prices. So these are my X's and these are my Y's. So the years that I'm comparing is 2010 and 2013. Is that doable? All right. So the change in my Y over the change in my X. So from 2013 to 2010. So we're looking here and here. What do I do? So my 2 Y's are my 2 Y's. So we have 3.57 minus 2.84 divided by, and now my X's are that I'm using. I can use 0 and 3. We can say 0 and 3. We can look at the ends. 1, 2. How far from 10 are we, right? Okay. If you wanted to, could you do 2013 minus 2010? Yeah, you're still going to get the same thing. Okay. So then we do the math. So this equals 0.73 divided by 3. So approximately, what is my average rate of change? So In terms of money, that would be 24 cents per year. Okay, since it's positive, what does that mean? It's an increase, right? It's a 24-cent increase per year in the gas price. Okay, I'm going to pause, and I want you guys to quickly go through and find the rate of change for 2011 to 2013 and 2012 to 2015, and check with a neighbor. All right, let's see how we did. So from 2011 to 2013, we're going to find our change in our Y. So that's $3.57 minus $3.58. And from 3 minus 1. So we're at a negative penny over 2 years. So when you put this in the calculator, did you get negative 0.005? Is there such thing as that in money? No. So in terms of money, what does that mean? A negative 1 cent. The 5 rounds to 0 to a. So it's decreasing a penny per year. If we chose those 2 points as our points of reference. Okay. And then if we did the last one, 2012 to 2015, you had $2.51 minus $3.69. And then you had 5 minus 2, which equal negative 1.8 over 3. So approximately negative 39 cents per year. If you were a consumer, which rate would you want them to use? The third one, right? I want that one that's going to give me the most decline every year, right? Does that make sense? All right. Yes. Are we good with average rate of change? All right. Now we're going to use average rate of change to create a linear system, a linear problem. Okay. How many of you remember us doing the old truck where you had to understand its value and its depreciation, and we compared it to whether it was linear or exponential? Which one would show us the best way of modeling that situation? Okay, that's what's happening here. Okay, so the first thing we said we need to do was create a table, right? So based on what we have here, it says that in 2020, there were 1,600 students. So in 2020, we had 1,600 students at Waco High School. And in 2022, there were 1,700 students at Waco High School. And it says, based on the average rate of change, predict the number of students enrolled at Waco High. So we have to find our average rate of change, which says that we are using our Y equals MX plus B. And our average rate of change is going to represent our what? Our slope, right? So to find our average rate of change, our change in Y over change in X. So we had 1,700 minus 1,600 divided by 2022 minus 2020. What do we get? 100 over 2, which is what? 50. So our average rate of change right now is 50 students per year, right? All right, so we now know that we have Y equals 50x plus B, right? How do we find our B? There we go. We're going to take what we have and we're going to plug it in and solve for our B. Remember, you got to find your B given you once you have your rate of change in your given data. So I'm going to plug in Y is what? 1600. X is 2020. And it's okay to use years when it's linear, right? When is it not okay to use the actual year? Anyone remembers? Exponential, because it grows super duper fast. Okay. All right. So we're at 1600 equals, what is 50 times 2020? 101,000. All right, you two. Here we go. What do I need to do to get B by itself? Subtract. One try. And what I do to one side, I do to the. So what is 1600 minus 1,100? Negative what? Yep. Equals our B. So now we have an equation that we can use to find for any year, right? So we have Y equals 50X minus 99,400. Okay, so that's our equation. And now what year did it want us to find it for? 2019. Can I just plug in and solve for that? Yeah, so we have Y equals 50 times 2019 minus 99,400. And what do we get? How many students were predicted? 1,550. 1,550 students. Good job. Okay, the key thing is once you have that average rate of change and you've created that equation to follow, you can make predictions about any other value, right? You just got to get there. I know it's been a while, but hopefully this is like, I've seen this before. All right, here we go. Now we're going to talk about exponential functions. Does anyone remember what the A represents in our exponential function? Yes, initial value. Good job. It is our initial value. It's where did we start at, right? So in terms of a car, what was the initial cost, right? What was it? What was its value? Does anyone remember what our B is? Our what? Our growth rate. It's either our growth rate or decay. So it's our rate of growth or decay. Okay? And it's always going to be subtracted from 100%. Subtracted or added to 100%. Our growth and decay rate. And your X is it's your independent variable, right? So it's your independent variable. Okay. So it could be the number of computations, your compounds, how much is going to happen. But typically it's going to always be our years, our time. Okay, so let's do an example. The value of the piece of factory equipment was 20,000 when originally purchased. Each year, the equipment depreciates by 10%. Write an equation that models the scenario after T years, then determine the value of the equipment after 3 years. So the first thing we do is identify our variables. What is our A? Perfect. What is our B? So it's 100%. It's depreciating. So minus 10%, which just makes it 90%. Okay. What is 90% as a decimal? 0.9. So that's our B. 100% minus 10. So depreciation, we're subtracting from 100%. Appreciation or growth, we're doing what to 100%? We would be adding, right? Okay. And then our X equals T. Do we have everything we need to create our function? Yes, we do. So we have y equals 20,000 times 0.9 to the t. There's your first part that it wanted, your equation. Second part is, what would be the value after 3 years? Can I solve for that? Yeah. So y equals 20,000 times 0.9 to the 3. So what is the approximate value after 3 years? 14,000 what, guys? 580. Yes, remember PEMDAS. We do our exponent, then we multiply. PEMDAS, exponents, then we multiply. How do you feel? Okay. All right. So the next part, we're gonna have to kind of wait to do tomorrow because I realize you don't have calculators at home. So it won't be as easy, but we're gonna have to go back through our regression models. Okay. Even though it says linear regression, remember it's the same steps that we would follow for all the others, except instead of clicking on linear, we would click on the quadratic and exponential. So I thought I was gonna be able to do this without you, but we got to go through the calculator tomorrow. Okay.